Imagine draining an entire lake using nothing but wind. No engines, no electricity, just wood, gears, and windmills slowly lifting water out of the land. That challenge kept Dutch engineers awake for centuries, and the answer they came up with was one of the most mechanically elegant solutions in history. A rotor with a dozen blades catches the wind. That rotation travels through a timber drive shaft, through a gear train, into a crank, and down a long transmission rod that moves a piston up and down inside a wooden cylinder. On every upstroke, water lifts. Slowly, relentlessly, for days and weeks at a time, until the lake is gone and the land below is dry. Geography. The Netherlands sits, on average, about a meter below sea level. In the low-lying polder regions, the ground can be 4 or 5 meters below the waterline of the canals running right alongside it. That is not a quirk of geography. That is the result of a deliberate decision made over several centuries to take land that was underwater and make it dry. The North Sea coast of the Low Countries was never stable ground. River deltas, tidal marshes, and shallow inland lakes covered most of what is now the Western Netherlands. The soil underneath was peat, soft, waterlogged, and prone to sinking the moment anyone tried to drain and farm it. And people did try, starting in the early medieval period, cutting channels and building earthen embankments to push the water back. The peat problem. The problem was that draining peat causes it to compress and oxidize, which means the land drops as you work it. The more successfully you drain, the lower the ground sinks, so you need to drain even harder just to stay even. There was no natural resolution to that cycle. The land kept falling and the water kept returning. Dutch communities built dikes to hold the sea and the rivers back, and those dikes worked for their intended purpose. But a dike only holds water out. It does not remove the water that is already inside. Rain still falls within the enclosed area. Water still seeps up through the peat. Without a way to actively lift that water up and over the embankment, the land behind the dike would simply fill back up season after season. The expanding lake. The Haarlemmermeer made this problem visible at scale. That inland lake, north of Leiden, covered roughly 180 square kilometers at its peak. It had swallowed entire villages over the centuries, growing larger with each major storm. It was not a natural feature that people managed around. It was an encroaching threat that grew more serious the longer it was left alone. The engineering question. So the engineering question became very specific. How do you continuously lift water from a low basin up over a dike and into a drainage canal using only the wind, reliably enough and for long enough to actually empty a lake? The Dutch solved it by turning entire landscapes into pumping systems. Canals, dikes, and windmills working together to lift water step by step out of the land. The answer required treating the land as a hydraulic system. Every field, every canal, every embankment connected into a single water-moving network that had to be kept in constant motion. The machine. That network depended on a machine. The concept itself was simple. But the machine had to survive constant wind, water, and mechanical strain for years at a time. Dutch millwrights built thousands of them. And because of that, the Netherlands exists as dry land today. Not through politics or agricultural ambition, but through mechanical engineering applied at a scale that had no precedent. Rotor and gear system. The rotor is where it starts. 8 to 12 wooden sail frames covered in canvas or wooden slats, catching the wind and beginning to turn. That rotation drives a horizontal drive shaft, hewn from a single timber, sometimes half a meter across, running through the cap of the mill and into the interior. What happens next is where the real mechanical work begins. Mounted on that drive shaft is the brake wheel. It is a large wooden gear, and its teeth are not cut from the wheel itself. They are individual wooden pegs, hundreds of them, driven into the rim at precise intervals. Those pegs meshed with a smaller vertical gear called the wallower, which sits at the top of a vertical shaft running straight down through the center of the mill. Why the gear train matters. The problem the gear train is solving is torque. Wind pushing on a sail generates rotational force, but that force is spread across the full diameter of the rotor, a very large circle. To push a piston against a column of water, you need that force concentrated, applied hard through a small mechanism against real hydraulic resistance. So the gear train steps the rotation down, multiplying force while reducing speed. Converting rotation to pumping. The vertical shaft carries that motion down to the pit wheel at the base of the mill. The pit wheel meshes with a horizontal crank gear, and that final stage converts continuous rotation into a reciprocating stroke. An offset crank pin pulling a long pump rod up and down with each full turn. That pump rod runs vertically down into a wooden cylinder submerged at the base of the mill. Inside the cylinder is a piston with a leather flap valve fitted to it. At the bottom of the cylinder is a second fixed valve. On the downstroke, water pressure from below forces the lower valve open and water floods into the cylinder. On the upstroke, that lower valve closes, the piston valve closes, and the full column of water above the piston is driven upward. Each stroke moves 10 to 30 liters, depending on the cylinder diameter and stroke length. At 8 to 12 strokes per minute, a single mill shifts several hundred liters continuously. Not fast, but it does not stop. Self-regulating valves. The leather valves deserve attention here. They are not mechanically timed. No cam, no linkage, no external control. They open and close purely in response to pressure. Water pressure below opens the inlet valve. The weight of the water above closes it. The pumping cycle regulates itself. So what you have is a piston doing the lifting, a gear train supplying the force, and two passive valves managing the flow. Dutch millwrights spent generations refining the gear ratios, the stroke length, the piston diameter, the valve geometry. And by the 17th century, all of it was being built from timber, leather, and hand-forged iron to tolerances that kept polders dry for years at a stretch. If you enjoy seeing how historical machines actually worked, the gears, mechanisms, and engineering behind them, consider subscribing. This channel explores the machines and mechanical systems that shaped the world long before modern engines or electricity existed. Gear reduction details. The brake wheel on a large Dutch drainage mill was 3 to 4 meters across, with over 100 wooden teeth driven into its rim. The wallower it meshed with had maybe 20 to 30. That single gear pairing multiplied torque by a factor of 3 or 4 while cutting rotational speed proportionally. So right there, before the motion has even reached the bottom of the mill, the wind's energy has already been reshaped. Less speed, more force. The second reduction stage, pit wheel to crank gear, stepped it down further. Combined, the full gear train reduced rotor speed by a factor of 5 to 8. What that means in practice is the crank turns slowly and deliberately, producing the long, steady pump strokes the piston needs to push water uphill against its own weight. Too fast and the mechanism beats itself apart. Too slow and the drainage falls behind. Getting those ratios right was the core engineering problem, and Dutch millwrights solved it through generations of careful, practical refinement. Wooden gear advantages. Wooden gear teeth were not a shortcut. They were a considered choice. Hardwood pegs driven into elm or oak rims wore predictably, and when one split or rounded off, a millwright could drive it out and fit a new one in an afternoon. An iron gear with a broken tooth was a different problem entirely. It meant pulling the mechanism apart and sending out for a smith. Wood kept the mill running. There was another advantage to wood that is easy to overlook. The pegs were slightly flexible. When a sudden gust hit the rotor, or debris momentarily jammed the pump, the wooden teeth absorbed some of that shock rather than transmitting it straight through the drivetrain. That small give in the gear mesh made the whole system more durable under exactly the kind of unpredictable loading that wind power produces every day. Alternative pump systems. Not every polder used a piston pump. Where the required lift was very shallow and the drainage channel was wide, a scoop wheel made more sense. A large paddle wheel that lifted water in a continuous sheet rather than discrete strokes. For steady, low-head pumping, the Archimedes screw offered another option. A helical blade turning inside a tube carries water upward between its flights and discharges it at the top. It could be driven directly from the windmill shaft with minimal gear reduction. What this variety tells you is that Dutch millwrights were not applying a single template. They were reading each polder, its water depth, drainage area, and required lift, and selecting the pump type whose mechanical characteristics matched the task. Steam replaces windmills. The Haarlemmermeer was not drained by windmills. By the time Dutch engineers tackled it seriously in the 1840s, steam-powered pumps had become reliable enough to handle a lake of that scale. But the hydraulic infrastructure they used, the ring dikes, canal networks, staged pumping systems, and engineering knowledge, all came from 2 centuries of wind-powered polder work. The system that drained lakes. The operational model had been established well before that. A ring dike was built around the target area first, cutting it off from surrounding water. Then drainage canals were cut in a grid across the interior. Windmills were positioned at canal intersections, each pumping water from the interior up into a higher ring canal that carried it out to sea. Where elevation differences were large, multiple windmills worked in stages, each lifting water higher until it could flow out of the polder. Managing wind power. Wind made that balance difficult. During calm periods, water levels rose and mills could not run. During storms, wind could overload the machinery. The solution was reefing, reducing sail area, and using the mechanical brake, a wooden band that clamped the brake wheel to slow or stop the rotor. Managing a drainage mill was skilled work. Millers lived on site, watching water levels through the night and adjusting sail area as conditions changed. The scale of the system. By the 1600s, draining lakes with windmills was no longer an experiment. It had become a full-scale engineering industry. At the peak of Dutch polder development in the 17th century, several thousand drainage windmills were running across the province of Holland alone. The Beemster Polder, drained between 1607 and 1612, required 26 mills working in coordinated stages to remove roughly 70 million cubic meters of water from a lake that had held that water for centuries. The Beemster is now a UNESCO World Heritage Site, recognized specifically for its geometry. The grid of canals, roads, and farmsteads laid out on the drained lakebed has remained essentially unchanged for over 400 years. When steam power arrived in the 19th century, it did not replace a primitive system. It followed a mature hydraulic engineering tradition built entirely from timber, leather, wooden gears, and wind. The windmill was not a pastoral symbol. It was a high-torque pumping engine moving millions of cubic meters of water out of the Dutch landscape over several centuries. Gear reduction, reciprocating lift, and passive valve control. Principles still used in modern hydraulic and wind energy systems. About 26% of the Netherlands sits below sea level. That is not a geological accident. It is a deliberate engineering project that began with windmills slowly lifting water, one piston stroke at a time,